Welcome to the subject of agronomy. This is Lecture 4, Part 2, on the topic of broadacre cropping management. This subject is part of the agricultural degree offered at North Melbourne Institute of TAFE, based in Australia. Please visit our website for further details on the subject, courses and education products that we offer at www.nmit.edu.au. My name is Dr. Nikki Cooley. This lecture is separated into two parts. In the first part we introduce broadacre cropping in Australia and ground cover management no-till. In the second part we will introduce the practice of soil sustainability in broadacre cropping. Please note it is advisable to watch part 1 before continuing with part 2. Land management affects soil condition. The condition of the soil contributes significantly to the quality of the ecosystem services a specific environment can provide. The condition of the soil contributes significantly to the health, growth and development of a crop. The condition of the soil contributes significantly to the profit that a farmer may make. And for all of these reasons, it is a major consideration, not only in the field of agronomy, but also in the subject. So let us start with the basic or an outline of soil condition issues. The most common, particularly in Australia, is the loss of soil, which is termed erosion. Typically, soil can be lost by wind and water. Soil can also be lost by slow rates of acidification and by soil carbon decline. It is worth noting that there are specific regional and soil type conditions which we are not covering in this outline. The figure on the screen is a visual summary of the differences that different land management decisions can make on ground cover and therefore loss of soil through wind erosion. Where you have poor management practice, you tend to have low ground cover. This enables dust to become present and declining resource in the soil. While when you have best management practice, you tend to have good ground cover, therefore no dust, and you improve or maintain your condition. The following map was produced by the State of the Environment in 2011 and shows a soil erosion grade for Australia. The scale varies from very poor to very good. Can you identify where the Yangying farm is located, and if this area is considered very poor or very good for soil erosion? Analysis of wind erosion resulting in soil erosion in 2009 indicated that around 1.29 million square kilometres, that's about 17% of the continent, may have been affected by widespread and moderate to severe wind erosion. Areas that are most likely to be affected are those where vegetative cover is low. The following map, produced by the State of the Environment in 2011, indicates location where improving soil and land management practices to reduce soil loss from wind erosion will provide the biggest benefits. So let us talk about soil pH management, or it's sometimes termed as acidification. As a plant material dies and decays, it adds organic matter to the form of humus to the soil. Humus improves soil moisture retention while affecting soil chemistry. Cations such as calcium, magnesium, sodium and potassium are attached and held to humus. These cations are rather weakly held to the humus and can be replaced by metal ions like iron and aluminium, releasing them into the soil for the plants to use. Soils with the ability to absorb and retain exchangeable cations have a high cation exchange capacity. Soils with a high cation exchange capacity are more fertile than those with a low cation exchange capacity. Hydrogen ion concentration in the soil is measured in terms of the pH scale. Soil pH ranges from about 3 to 10. Pure water, for example, has a pH of 7 and is described as neutral. pH values greater than 7 are described as alkaline or basic, while pH less than 7 are described as acidic. Most good agricultural soils have a pH between 5 and 7. The definition of pH. pH is defined as the negative logarithm of the hydrogen ion H+ concentration. When water ionizes to hydrogen plus and OH minus a neutral solution, both hydrogen plus and OH minus ions are in equal concentrations. That's about 0.000001 moles per litre, thus a very small concentration. It is estimated that 1.4 million square kilometres of Australian soil, about 19% of the continent, has a problem with acidification. There is a high risk the more intense the agricultural system is. The following image gives an idea of soil pH ranges. The range of a common pH for humid region soils is between 5 and 7. The range in pH for most inorganic soils can vary from 3 up to 10. This is a significant range. The range in pH for arid region soils tends to be more alkaline, from 7 to 9. The pH of the soil is one of the fundamental soil properties that gives us information about governing nutrient availability, metal mobility, elemental toxicity, microbial activity, and, most importantly for us, plant growth. The soil pH can be defined by whereabouts in the soil profile the soil comes from. For example, in agronomy, we are most interested in the pH of the topsoil. This is the soil at the very top, all the way down to the first 0.1 metre depth. Another area of interest is the subsoil, and this is approximately 0.6 to 0.8 metres deep. In 2011, some soil scientists from CSIRO published a paper on the pH of Australian soils. This was conducted as part of a field survey on a national scale. Floodplain soils collected near the outlet of 1,186 catchments, covering about 80% of Australia. This is an important survey, as you can see different areas represent different pH scales. There are strong indicators of precipitation and leaching with respect to the pH, i.e. low pH along the coastal fringes and high pH in the dry centre. Where it is very arid, there is high pH. Vegetation tends to reflect lower pHs, especially where organic matter is abundant. Regional scale decision making relating to agricultural, environmental and infrastructure and mineral exploitation decisions were concluded by the authors to be very important when making decisions on how you manage the soil. So if we examine the findings from the Caritate et al. 2011 paper, we see some trends from Australia's pH soil profile emerging. Examining the medium data, we see that the medium topsoil pH is 6.5, while the subsoil pH is about 7, although this tends to fall into two trends. It either ranges from 6 to 6.5 or ranges from 8 to 8.5. The outcomes from this paper suggest that the distribution of soil pH at the national scale indicates strong controls exerted by a number of factors, such as precipitation, leaching, particularly along coastal fringes where low pH is found and high pH is found in the dry centre, how arid the community or environment is, the vegetation with low pH reflecting abundant soil carbon matter, and the subsurface lithology, that is, high pH over limestone bedrock. I have placed a link on Moodle where you can directly access this map. Look at this map and identify if the Yang Ying farm is at low, medium or high benefits of soil management. In a separate survey, CSIRO Land and Water 2009 produced a pH map. This is indicative locations where improving soil and land management practices to manage soil pH will provide the biggest benefits. Now let us spend some time on the very important component of soil carbon. Soil organic carbon is a complex and varied mixture of materials and makes up a small but vital part of all soils. Soil organic carbon is sometimes abbreviated to SOC. Soil organic matter is decaying plant and animal material, and carbon is a part of this. Matter that hasn't decomposed or is undecomposed is not part of the soil organic matter or the soil organic carbon. Soil carbon has been separated by CSIRO into 4 categories. The first is crop residues. This is components such as shoot and root residues which are less than 2 mm found in the soil and on the soil surface. Particulate organic carbon are individual pieces of plant debris that are smaller than 2 mm but larger than 0.053 mm. Humus is decomposed materials less than 0.053 mm that are dominated by molecules stuck to soil minerals. Recalcitrant organic carbon, this is biologically stable, typically in the form of charcoal. Each of these components of soil carbon has different functions. Crop residues are broken down, and these residues release energy to the environment and the microbes in the soil. Particular organic carbon is broken down relatively very quickly. Particular organic carbon adds to soil structure. It also aids in the release of nutrients and provides energy to this community. Humus' function is to release nutrients, particularly components like soil nitrogen. And recalcitrant organic carbon, which is also referred to as a biochar, is the product of burnt carbon-rich material, for example charcoal, and this decomposes very slowly. Looking at some trends of soil carbon, good soils typically have 10% or greater carbon. Poor soils or heavily exploited soils tend to have less than 1% carbon. The content of carbon in the soil can be management dependent. This is important because different fractions decompose at different rates and contain different quantities of nutrients. Managing soil carbon is a balance. It is a balance between the inputs of new plant and animal material and the constant losses where the carbon is decomposed and the constituents separate to mineral nutrients and gases, or are washed or leached away. Typically, carbon levels build up where water, nutrients and sunlight are plentiful. Carbon is lost where microbe activity is high, such as in warm, moist environments, and where there are fallow periods with no plant inputs. There are many factors which can lead to loss of carbon in the soil. These include decomposition and conversion of carbon in plant residues and soil organic matters into the gas carbon dioxide. There are many factors which can lead to this carbon loss. These include the type of plant and animal matter entering the soil, climate conditions, particularly rainfall, temperature and sunlight, the soil clay content, fallowing, cultivation, stubble burning or removal of stubble, and overgrazing. Now we have looked at some of the components that cause carbon loss. How can we gain carbon in our soil ecosystem? Carbon gain is dependent on the type of plant and animal matter added to the soil. You should note that plant organic matter makes up the majority of carbon gain in the soil. The quantity of this matter also is dependent on how much carbon ends up in the soil. Interestingly, fire can result in an end product of charcoal. This contains carbon, and once this enters the system, carbon can be gained. However, fire can also result in the loss of carbon via release of the gas carbon dioxide. Any management practice that enhances the plant residues will increase carbon. Fertilizer application, improved rotations, improved cultivations, irrigation, crop intensification, reduced tillage or no tillage management practices, as well as the addition of organic matter such as manure, plant debris, composts and biosolids can all result in improved and higher carbon gain concentrations in the soil. So why carbon gain? Why do we need to be concerned about this in agronomy? Well, there are another number of components of the soil organic matter that are changed by improving your soil carbon. Let's start with the biological functions of soil organic matter. Nutrients are released and they provide a habitat for soil organisms. Energy is released for the biological processes of these soil organisms. And biological functions of soil organic matter contribute to soil resilience. That is, the ability of the soil to return to its initial state after disturbance, for example after tillage. The chemical functions of soil organic matter are important because it is a measure of nutrient retention capacity in the soil. It allows for pH change resilience, and it is a store of the main key nutrients, especially nitrogen and potassium, which are very important for plant growth. Soil organic matter also contributes physically to the soil. This is in the forms of soil structure stability, as it's improved by binding soil particulates into aggregates, improved water holding capacity, and there is some temperature moderation of the soil. The improved water holding capacity is particularly important for cropping, as is the soil temperature moderation for summer cropping. The following diagram from Fusion Farms illustrates the difference between holistically managed land and conventionally managed land with respect to carbon dioxide and carbon flows. You will see from the conventionally managed land that much CO2 is lost from the soil to the environment and very little replaced. Where in the alternative there are more roots, more carbon is stored, and less carbon is lost to the atmosphere. It has been estimated by the NRM that 838,850 square metres, which is approximately 11% of the continent area of Australia, has been identified as having moderate to potential to store more carbon. This map here illustrates some of these areas. Can you identify, by looking at this map, if Yan Ying Farm is in a location to provide low, medium or high benefits of improving soil carbon? A paper termed Cover Crops and No-Till Effects on Physical Fractions of Soil Organic Matter was published in Soil and Tillage Research in 2013 by Nascentry et al. This paper can be found on Moodle. Please take some time to read it after this lecture. The objective of this study was to evaluate the effect of cover crops on total organic carbon, TOC, and the physical fractions of soil organic matter in soil under a no-tillage system and a conventional tillage system. 3 years of experimentation was implemented a number of cover crop using rice and cover crop rotations. Treatments included cover crops such as Pansium, Brachia, and pearl millet, fallow, till and no-till. The results of this paper show that no-till resulted in higher levels of free light fraction carbon and intra-aggregate light fraction carbon than with the conventional tilling system. Results of this study also showed that rotations with millet showed the highest carbon and highest nitrogen levels in the soil. To conclude, cover crops accumulate more TOC and total nitrogen in the concentration of the heavy fraction as well as the lighter fractions of the soil. This is the most recent paper I could find in July 2013 on this topic, and there is mounting evidence to suggest that understanding your management, both your plant type and your type of management with respect to till and no-till, has significant impacts on the carbon concentration in your soil. A second paper I'd like you to take some time to read, which will be on Moodle, is the impact of 14 years of conventional and no-till cultivation on the physical properties and crop yields of a loam soil at Griffin, New South Wales, Australia. This article was written by So et al. And published in the journal Soil and Tillage Research. One of the observations I'd like to highlight in this research was that soil physical properties after 14 years of cropping showed increased organic matter in the no-till compared to the conventional till. This can be related to improvements in soybean yield. These were not observed in the initial periods of the experimentation, 1981 to 1985, but were seen in years post-1987. Yields were typically 2.14 tonnes per hectare in the no-till, compared to a reduced 1.67 tonnes per hectare in the conventional till. This demonstrates two components. One is that the management of your till can improve your crop productivity, and secondly, that this management can take some time before you see these results. The following table, produced by CSIRO, is a summary of how different practices can result in increasing different components to soil sustainability. These categories include increased carbon content, reducing risk of wind erosion, reducing risk of water erosion, and reducing the risk of soil acidification or lowering the pH. In this table, the practice of no-till is compared with stubble left intact, reducing fallow, soil pH testing, lime application, monitoring of ground cover, use of ground management targets, pasture phase and crop rotations, and increasing perennial pastures. They are also associated with the types of agriculture, from broad-acre cropping to beef and cattle sheep grazing, through to dairy. This is a good summary and would be worth taking some time to note and learn the contents. This brings us to the end of Lecture 4, Part 2. In this lecture you have learnt what sustainable soil management involves. You have learnt all about the major inputs, carbon, pH or acidity, and erosion caused by either wind and water. You have understood how these affect Australian farming, and how improvements might be made to certain areas of Australia to improve certain components. We have talked about management techniques and how they may be employed to improve your carbon, reduce your acidification, and reduce your erosion by either wind or water. All of these techniques can be brought together to build resilience into your soils. This should enable long-term increases in productivity in your yield and therefore your profits. In the next tutorial, I would like you to take some time to discuss how the concepts covered in this lecture can be applied to the Yin Yang Farm Teaching and Research Demonstrator. Is this demonstrator affected by either wind or water erosion? Does it have pH acidification problems, and do you suspect the carbon level is low, medium or high? If any of these are the case, how would you go about managing to improve these? This brings us to the end of this lecture.